speaker for lunch is Andreas Brandstaedt from the University of Rostock, and he's going to talk on leaf powers.
Thank you very much, and thanks for the opportunity to give this talk here at the workshop in Cambridge. And it's a great pleasure to be the first time in Cambridge. So I want to give you an idea of leaf powers, which is closely related to graph theory and has its background in phylogeny and phylogenetic trees. And it certainly doesn't have much implications for biology and for phylogeny, but it's very interesting for graph theory and algorithms. So the concept came, I told you my coordinate. The concept came from phylogeny. And so, for instance, if you look at a survey paper by Tandy and Kim, but I don't have to tell you what a phylogenetic tree is, but normally you have species or taxa which are at the leaves of some tree, and they are close to each other if their distance in the tree is small. So which means, I think we can skip that. It means that you can generalize in a mathematical way and look at so-called phylogenetic K-root and Steiner K-root, which definition came up in a paper by Lin, Kearney, and Jian in 2000. And they defined that a tree with leaf set V for a finite undirected graph G is a phylogenetic K-root of G if the internal nodes of T have degree at least 3. They are branching events. And you have this distance requirement. X and Y have an edge, are adjacent in the graph G if and only if their distance in the tree is at most K. So you have two conditions. You have the distance condition and you have this branching condition. Internal nodes should have degree at least 3. And what is known, there are corresponding problems. So given a graph, is there such a phylogenetic K-root of G? So far you fix K, and this can be solved in linear time for K at most 4, and it's widely open for K at least 5. But this is not about leaf powers. Leaf powers is a similar concept. And you can also look at the variant, which is called Steiner K-root, where you do not only have the species at the leaves, but you have it at internal nodes as well. And now we can come to leaf powers and leaf roots. Nishimura, Rakte, and Tillikos modified the concept in a paper which appeared in 2002 in Journal of Algorithms, where they drop the condition that internal nodes are branching nodes. They can have degree 2. So now you have only the distance condition. A graph, a finite undirected graph G is a K-leaf power if there is a tree T with the leaf set of T is the vertex set of G, and you fulfill the distance condition. X and Y, vertices X and Y of G form an edge in G if and only if they are close to each other in the tree. And such a tree T is called a K-leaf root of G. This is a very natural concept, of course, but now you have two types. Close species which are close to each other and species which are not. So now you have binary distinction. Now you can generalize, you can say a graph is a leaf power if there is a K such that it is a K-leaf power. So you just take the union over all these classes. And what about two-leaf powers? Two-leaf powers are a very simple type of graphs. Two-leaf powers mean that if you have different vertices X and Y, they have the same predecessor in the tree. The distance is at most 2. They have the same predecessor. That means they are twins. And now a two-leaf power is exactly a disjoint union of cliques. All the vertices with the same predecessor form a clique, and cliques are disjoint. So two-leaf powers are nothing else than disjoint unions of cliques. That's very simple. Here's an example. Is this a two-leaf power? No, it is not the disjoint union of cliques, but it is a three-leaf power. This graph with vertices 1, 2, 3, 4 on the left has a three-leaf root. The distance between 1 and 2 is at most 3. It is 3. Between 2 and 3 is 3. Between 3 and 4. But between 1 and 3 is 4. So 1 and 3 are not adjacent. 1 and 3 are not adjacent. And 1 and 4 are not adjacent. 2 and 4 are not adjacent. So this is a three-leaf root. Very simple example. Here's another example. Again, a three-leaf power which has, for instance, this three-leaf root. So these are examples for three-leaf powers. And now let me come to a background, a graph theory background, which was mentioned yesterday already. Tandy mentioned the so-called triangulated graphs. Triangulated graphs come up in many places, in many examples. And sometimes they are called triangulated, sometimes chordal, sometimes rigid circuits. These show up so frequently and are so important, for instance, in relational database schemes where it's closely related to alpha acyclicity of hypergraphs. So a graph is chordal if it contains no chordless cycle of length at least 4. So on the left side you see the chordless cycle of length 4, here's length 5, here's length 6, and so on. So these chordless cycles are not induced subgraphs. There are many characterizations of chordal graphs. For instance, bi-click separators, bi-click trees, which means a tree structure of the maximal clicks of these graphs by simplicial elimination orderings, by intersection properties. They are the intersection graphs of subtrees of a tree, and so on and so on. There are various books which describe these graphs, for instance, Mardigal Lambic's book on algorithmic graph theory and perfect graphs, and so on. So let's have a look at graph powers. Since we have this distance condition in the tree, it is closely related to graph powers. The usual concept of graph power is that the kth power of a graph G has the same vertex set, and two vertices x and y are adjacent in the kth power if and only if their distance in the graph is at most k. This is the kth power. And k-leaf powers are closely related to the kth power of a tree. So if you want to learn more about k-leaf powers, we have to look at powers of chordal graphs. We have to look at powers of trees. And it's well known that powers of trees are chordal, but one can say more on it. One can say much more, since they are not only chordal, they are also strongly chordal. Strongly chordal graphs are a subclass of chordal graphs where so-called suns are forbidden. A sun consists of a central clique and some vertices outside which have exactly two neighbors in the clique, and here you have the examples of the 3-sun, 4-sun, 5-sun, and so on. So strongly chordal graphs are simply sun-free chordal graphs. Again, there's a close relationship to alpha acyclic, to the relational database schemes. They correspond to beta acyclic hypergraphs, which means somehow hereditary alpha acyclic hypergraphs. Very nice concept, introduced by Martin Farber and treated by him and others. There are many nice results on it. I don't have time to go into details. For us here, it's important that strongly chordal graphs are closed under powers. The power, any power of a strongly chordal graph is strongly chordal. which is not true, by the way, for chordal graphs. The square of a chordal graph can be a non-chordal graph, C4, for instance. So what we have is, as an implication, we get that k-leaf powers are strongly chordal. These graphs are strongly chordal. The next question could be whether every strongly chordal graph is a k-leaf power for some k. And for a while we thought that this would be an open problem, but actually it's solved. You can use some background tools. For instance, this is described in a paper by Bibelniks and Daring on neighborhood subtree tolerance graphs based on a lemma by Bruyne and Lowe, which is dealing with totally balanced matrices, which is again very close to strongly chordal graphs. And finally it turned out, if you combine all these tools, you finally get the fact that there are strongly chordal graphs which are no k-leaf power. So this is a strict inclusion. Here's an example. This graph is a strongly chordal graph. Exercise, you can see it quite easily, but one can prove that this graph is not a k-leaf power for any k. You can construct other examples based on this principle. Now let's have a quick glance at 3- and 4-leaf powers. In the paper by Nishimura, Wakta, and Tilikos, 3- and 4-leaf powers were recognized in polynomial time, but the algorithms were quite complicated. There is a characterization of 3- and 4-leaf powers. It is again open for k at least 5. So far there is no characterization of k-leaf powers for k at least 5 and of leaf powers in general. But for 3 and 4, one knows a little more. And for this, I think I will skip this concept here. Critical clicks, this time is running. Let me skip this. Here are the forbidden subgraphs for 3-leaf powers. And the theorem is that G is a 3-leaf power if and only if G is full, dot, and gem-free chordal. Again, the tiny subclass of chordal graphs. If and only if the critical click graph is a tree. One can say even more. One can quite easily see that a graph G, a connected graph G, is a 3-leaf power if and only if it results from substituting clicks into the nodes of a tree. That this is very tree-like. And you also get linear time recognition for 3-leaf powers. And what is known for 4-leaf powers? For 4-leaf powers, it becomes more complicated. Now, here are 8 forbidden subgraphs. Again, there's a forbidden subgraph characterization. There's a theorem by Dieter-Raudenbach saying that a graph G without 2 twins, technical restriction, is a 4-leaf power if and only if it's G1 to G8 free chordal. One can analyze this a little more. One can see that the first 5 are responsible for squares of trees. And this seems to be a new result. G is the square of some tree if and only if G is chordal 2 connected and G1 to G5 free. And the last 3 are the gluing conditions for the blocks, for the squares of the trees. The squares of the trees are the blocks in these graphs. So this is, I think my time is over. I have to run. I still have some results. So now you can modify. Characterization for k at least 5 of k leaf powers is unknown. If you have an unknown problem and it's so stubborn, then you try to modify the problem and solve some simpler problems. Here's a modification. The graph is a KL leaf power if edges xy have distance at most k and non-edges xy have distance at least L. And of course you can modify this, but it makes sense. Since there is a paper on strictly chordal graphs by Kennedy, Lin, and Jan in 2006, which investigated these strictly chordal graphs, which were defined in a very complicated way by hypergraph conditions. And finally, it turned out that these are the dart gem-free chordal graphs, so a larger class than 3-leaf powers, but less than gem-free chordal. It turns out that these are exactly the 4-6 leaf powers. And therefore, I think we have a useful concept here. And now you can play the game here and look at all these classes. And the diagonal are the leaf powers. Here are the leaf powers. And only these 3 cases are known. And here you have all these KL leaf powers. And you can say a lot on it. We have some non-trivial results here. So, for instance, the characterization of 6-8. 4-6 is strictly called 6-8. Again, has a characterization by forbidden subclass. Okay, this is a very short glance at KL leaf powers. And finally, let us look again at the hierarchy. So we have these strongly chordal graphs. Every K leaf power is a strongly chordal graph. What about an even smaller class, gem-free chordal graphs, which corresponds to gamma acyclicity for hypergraphs? So this is the hierarchy from the relational database schemes. Fagin described it in the paper: gamma acyclicity, beta acyclicity, alpha acyclicity. Gamma acyclicity corresponds to gem-free chordal graphs. It turns out that every gem-free chordal graph is a K-leaf power for some K. For strictly chordal graphs, the K is 4. Can one limit it here? Turns out no. If you define the leaf rank as the minimum K, which gives you the K leaf power, then it turns out that Ptolemaic graphs have unbounded leaf rank. So this is quite an interesting hierarchy. But the problem of characterizing all these K leaf powers is widely open, and thanks for your attention.
Just one question. Those results about the forbidden subgraphs, are they actually a subgraph or a minor subgraph?
Induced subgraph,
okay.
Not minor.
Okay, well, let's thank all of the speakers this morning before we head out the door.